right after.
Oh, okay. Okay, yeah, I'll be there tomorrow morning. I usually get here around 9 o'clock.
I know, it's because I have iron from last time. I did. Just how it always went.
I lived on the floor. And I didn't notice. I didn't.
Do like the final one. Oh, wait, what? Where do you get them? Oh, she graded.
Yeah.
She graded them. That's actually coming from. We're gonna get them. So I can guarantee I will.
By any chance, do you still have the cheat sheets from midterm?
Midterm one, it could probably, I don't think I would have thrown them away, so it's probably in my office. I kind of just throw everything into a drawer, so if you want to come by and look through them. Yeah.
Thanks.
Mhm.
I'll wait. Yeah, I guarantee.
Yep.
Would you like a Tootsie Roll, Starburst, or a lifesaver?
I'm good. I'm good. Thank you, though.
Section.
All six of these, all six of these.
So the shared ends. No, I mean.
Oh, it's choice.
It's just. Yeah, they don't.
Hey, Kevin. Hey. All right, it's 2:30, so let's go ahead and get started today. Today is the final day, so last day of the semester for us in lecture. So how's everyone doing on our last day today? Mixture of emotions, as it always is on the eve before finals week. So okay, so as I promised today, we're not going to cover any new content today. Today I'm just going to be doing some review. Okay, so this is going to take the place of the usual, usually before an exam for this class, I record a review session. So this is kind of taking the place of that. So we were able to end everything kind of one lecture early, and so we're going to be able to spend today just reviewing stuff. Okay, and so based on the poll results, like I looked at them, like 10 minutes before I got here. The two winning results were, number one was radial heat conduction. And so that goes way back to kind of the beginning of the class. So I think that'll be good to review. And then the second most winningest one was the radiation exchange. Okay, so that's the most recent stuff. And I'm guessing people would like just some more help with the homework. Okay. So I'll definitely get through those two. I believe the third topic that was up there was external flow convection. So we have time at the end of the day. I'll review a bit of that. Although I forgot to bring the notes for that today. So, okay. And so just for your information, again, here's all the final exam information, just because this will be the last time that we all meet together. And so the final exam is a week from today. It's going to be in this room, E201. It's going to take place 3 to 4:50, so about 2 hours for the exam. And the materials that you can bring are your writing utensil, your calculator, and your 2 cheat sheets. Okay? And so if you have your cheat sheets from the previous exams, you can definitely feel free to use those. Don't feel like you have to make new ones. But keep in mind that, from the first 2 midterms, I did take off some content. And so there's some content that was on the first 2 midterms that's not going to be on the final. Okay? And so if you are going to be using your cheat sheets from the first 2 exams, you might have some wasted space there, because that stuff's not going to be on the exam. Right? And so as always, the first place you should check is the study guide, just to see what's going to be on the exam. So even though you don't have to, but I do recommend that you make your cheat sheets new, based on the final exam study guide, just so you kind of maximize that space. Okay, so any questions on just logistics or anything before we begin today? Okay, all right, so I actually do want to spend a couple minutes today, just filling out SOQs, just because I haven't mentioned it yet. And so SOQs for this class are due on Friday. And so, just because we have, a lot of people here, maybe not everyone, I want to take the first, 2 or 3 minutes today, just so you guys can fill it out. Okay, so I'm gonna go step outside, because I'm not allowed to be in the room here, because I can't be like, are you rating me well today? Oh, so I can't be here. And so, I'll go ahead and step out for the next 3 minutes. You guys can go fill out the SOQs. If you're on Zoom, of course, you can use your computers, but if you're in the class, you can use your phones. And if you don't want to fill it out today, that's fine too. I'll send an email today reminding everyone, but I do want to leave some time for you guys to do. Okay, so I'll be back in about 3 minutes.
So did I.
335. Hey, was
We're thinking about oh, you told me about it. Alex. Yeah.
Major strengths.
That'd be cool.
we could use eggplants like quarter shells. Or like sponge.
A small one. No, that's you can just have to talk to find out.
This for Jessica.
Oh.
I'm gonna do it for my presentation.
If we do a tradition, I think the board is swinging will like just tilt the whole room. We'll have to.
Yeah.
You might make the wheelbase unit like wider.
I'm halfway through.
And I never will.
You have
a square across to the bottom, so it doesn't hit the wall. Like if it tries to tell the floor, so 6 hours to finish. No. Exactly what.
Yeah, I was gonna say, literally, hairspray, like a can of hairspray for use, and then like an electric igniter. Sorry, yeah.
No, that's.
Yeah. Let's go.
He's like, what? Why? What's wrong with it? No, get it from
You also need
a really small one from oh no,
No, we're talking like yeah, because I want to make a potato can with it, but like that specifically, because I want like a decent sized barrel, and then just have the electric igniter at the end, so it doesn't do anything fancy. It's just like the cover at the end.
We'll get a button.
Yep.
I'm trying to remember.
I don't know.
But we're in the school.
Okay, all right. So hopefully you guys had time to write the review. So thank you guys for filling out the SOQs. I've been my SOQ, yes. Well, if you didn't, I'll send an email reminder. You can do it at home, right? So thank you guys. I mean, it's I've been doing this for about 3.5 years now, and so teaching is something you never really get good at. I've learned that over the time here. So but you can always keep getting better at it. And so the SOQs are basically my main way of it's basically, think of it as your way of grading me how I'm doing. And so I always take those grades and I always try to improve it, semester to semester. So so the more information you give me, the better, the more comments, it's always good for me. So thank you guys for showing. Okay, so let's get started with our review. Let me go ahead and zoom in a bit. Okay. So the first topic of review today is going to be steady state conduction in radial systems. This goes all the way back. Okay, so this goes back to our very first unit of the class, which was conduction in solid systems. Okay, so let me just start with that. And so when we talk about conduction in this class, what we really mean is heat transfer in solid matter. Okay? Okay. And so when we talk about heat conduction in radial systems, specifically what we mean are heat transfer in cylindrical systems and spherical. And so we kind of covered both in these other lectures. Okay? Okay. And so for the final exam, we covered a lot in our conduction unit. And so we started with planar systems, then we went to radial, then we talked about fins and transient conduction. But for the final exam, I chose to focus on just those first two units, which is just conduction in planar systems, conduction in radial systems. And there are two main types of information that I want you guys to get out of this. And so in those kind of first about 3 or 4 weeks of the semester, we primarily covered first of all, heat equation type problems. Okay. So those are problems where we basically solve for solutions to the heat equation. Okay. So that was our differential equation. We applied assumptions, we simplified it, and then we got the general solution, applied boundary conditions, and so on and so forth. Okay. So that's one type to know. The other type of problem to know is thermal circuit type problem. And we've been doing thermal circuits throughout this entire class, but in the first unit, that was kind of where we did kind of more pretty complex systems with 4, 5, 6. I think we did one with 6 before, different resistors. Okay, and so you should be prepared for both of these kinds of questions for the exam. So let's start with heat equation, because I think that's probably where a lot of people are going to want to see some review, because we've done thermal circuits quite a bit throughout the class. Okay. And so heat equation type problems, the way we start these is that we start with the general form of the heat equation. Okay. Okay. And so, of course, our heat equation is a differential equation. And the objective of these types of problems is to solve this differential equation to get a temperature distribution of some kind. Okay. So that's the objective, right? And so what I mean by temperature distribution is some function that describes what the temperature or how it changes as you travel throughout the medium. Okay, and so it's always going to be some function. And so for radial systems, this is usually temperature as a function of R. Okay. And even though we're not reviewing it today, but for planar systems, this is usually temperature as a function of X. Okay. And so if you come across a heat equation type problem, know that your goal is some function. Okay? So let's go over cylindrical systems first. So because depending on what type of coordinate system that you're in, it's going to have a different heat equation, bless you, that you have to solve for. Okay? Okay, so this is the cylindrical form of the heat equation. And so we have 1 over R, partial R. And let me give you the full one first, which of course we're going to simplify with assumptions. Okay. So that's the full form of the heat equation in cylindrical coordinates. Okay. You're never going to be solving this entire thing, but it's important to kind of know where we start because we're going to cross out a lot of these terms from our assumptions. Okay. So that's always the first part. And so, whenever you're doing heat equation type problem, you're going to start with the full equation and you need to list out your assumptions in order to help you simplify the equation. Okay. All right, number 1. So the first assumption that we always make is that we assume steady state. Okay. And so the steady state assumption lets us get rid of any derivative with respect to time. And so that's going to be this term right here. Okay. All right, so the only time derivative that we have is just the rightmost term, and that's going to get rid of that. Okay, number 2. So the number 2 assumption is that we're going to assume we have no variation in the polar angle. Okay. And so that assumption is called the axisymmetric assumption. Okay, so under the axisymmetric assumption, anytime you have a derivative with respect to angle, which here is a phi, then we're going to cross that out. Okay? So here we have one of such of those terms. So we're going to cross out that guy right there. Okay. Number 3, we are going to assume that we have no dependence on z, and so in other words, we have a fully developed solution. Okay, so partial z is going to be equal to 0. And so that's going to cross out that term right there. Okay. And so those 3 assumptions, we always apply for our system, because otherwise it becomes a PDE and it actually becomes impossible for us to solve. Okay. And so number 4 is an assumption that we sometimes make. And so, it depends on the problem. And so that sometimes boundary condition or sometimes assumption that we apply is with regard to the thermal generation. Okay, so our thermal generation, it's easy to lose him, but it's just this term right here. So it's the Q dot. And so sometimes, depending on our situation, we can assume that this is 0. Okay. But that one is on a problem by problem basis. And so that one you're going to have to read the problem. And usually the problem is going to be very clear to you about whether that should be included or not. Okay. And so some key words that you would you should look out for in the problems is that if the problem explicitly says that the material is producing heat, okay, Another thing that you might hear is that the material might absorb heat, okay? And so in those situations, if the material produces or absorbs heat, then the thermal generation term will be active, okay? And so if you see that kind of language in the problem, that means you should keep Q dot, okay? And so you're gonna keep that in your problem solving. On the opposite side, if you, for me, usually I'm very clear that the material does not produce heat, and I underline it and I bold it just so that you know. But some other types of language that you can find is, the material is non-reacting. Okay. Because usually the way that you produce heat in a type of material is that there's some kind of chemical reaction going on. So, probably the most easy example is like a heat pack, right? And so for a heat pack, that's made of a certain chemical where, if you kind of break it like that, then it starts producing heat. But if it's non-reacting, that means you don't produce heat. Okay. And so if we apply all these assumptions, all we're left with is 1 over R, partial R, KR, partial T, partial R. Okay. Well, I guess, we can transform these into regular derivatives if you want, but, I'll go ahead and just keep it for now. Okay. Plus Q dot is equal to 0. Okay. And so now what you have here is, now that we've gotten rid of most of the other derivatives, right? I'm gonna go ahead and change these to regular derivatives. Okay. What we have here is an ordinary differential equation, which you can solve for by just integrating, okay? Okay. And so after you integrate this, you're going to have what we call a general solution. And so the general solution is going to have some unknown constants. And then what we're going to do from there is apply boundary conditions to solve for those constants. Okay. Any questions on this so far? Yeah.
Can you explain the difference between thermal generation and having a heat flux?
Yeah. So heat flux, that's a good question. And so thermal generation is, something that happens within the material itself. And so if the material, like say you have like a ball, the sun is a good example actually. So the sun is made of like a material which it itself is producing heat. Heat flux, on the other hand, is something that you apply on the outside. So heat flux is usually heating from just the outside going in. Yeah. Mm-hmm. Okay, so let's do an example. I don't know if I have a, here's a good one. I think this is an example that we skipped in the class, but I think it's a good example of boundary conditions. Because I remember, when we went over this, I think boundary conditions was still a bit confusing. So let's do kind of a somewhat complex example here where we can see how the boundary conditions are applied. Okay, so we have a cylindrical system here. Okay. It's going to be a hollow cylinder. We have an inner radius Ri. We have an outer radius Ro. Okay. What we're saying is that we have no generation in this case. Okay, so we're going to set Q dot is equal to 0. And in terms of boundary conditions, on the inside here, we have a prescribed heat flux, or in this case, a heat transfer rate. Right? And so this cylinder is being heated from the inside by a heat transfer rate of Q dot, okay? And so this Q naught here will have units of watts. And on the outside of the cylinder, we're going to have convection cooling. So we have convection out here. And then we have, T infinity and H. Okay. And so on this problem here, what we're interested in solving for, we're interested in solving for the temperature distribution inside the cylinder as a function of R. Okay. So let's go ahead and start with our assumptions. So first of all, we assume that we have a 1D situation. And so the 1D situation just basically means that it combines both axisymmetric and no Z dependence. Right? And so the only free variable that we have is the radius, okay, or R. Okay, 2, we have a steady state situation, just because we always assume that. And in this particular problem, just because the problem said so, we have no thermal generation. Okay. Right. Yeah. So in this particular case, I kind of shortened the problem description, but the problem basically says that the cylinder is not producing heat, and so if that's the case, then you say no generation. Yeah. So you can have heating from the inside and generation as well, but it's just you have to kind of read the problem to say that this one in this particular case we have no generation. Yeah. Okay. So before we start solving, let's go ahead and list out our boundary conditions. And so first we have the boundary condition at Ri. And so at Ri, we have a prescribed heating rate. Okay. And so for this types of boundary conditions, we use our Fourier's law. Right, so remember Fourier's law sets that minus K times A times dt, in this case is dt dr. Okay. All of this applied at R is equal to Ri. Okay. This is equal to our heating rate, Q naught. So that's the first boundary condition that we're going to apply. Because again, if you look at the situation at Ri right here, we have a heating, we have applied heating that has a magnitude of Q naught. Okay, and so mathematically, the way that we apply that is through Fourier's law. Okay. And so on the other side, we have convection cooling. And so for this, we're going to apply Newton's law of cooling. An equation that we've used many, many times throughout this class. But here we're going to use it to apply our boundary condition. Okay, so Newton's law of cooling basically says that Q at R is equal to R naught, or RO, excuse me. This is equal to H times A times TS minus T infinity. But instead of TS, instead of the surface temperature, we're going to plug in our temperature distribution applied at R naught. Okay? We have T at R naught minus T infinity. Okay. And so this T at R naught, this is the same as TS. And because we're working with the heat equation type problem, we can't just say Q over here. And so we have to set this equal to Fourier's law as well. And so we're going to say minus K times A dt dr at R is equal to R naught. Okay. So these are our two boundary conditions. Right? Remember, when you're doing these heat equation type problems, you have to really look at the figure. You have to really look at the problem to determine what your boundary conditions are. So if I remember correctly, when we were going through this the first time, a lot of people would look at a situation like this and just say that our boundary condition was, T at Ri is equal to Ti or something like that, right? I think just because, we did examples like this in the class, but something like this would not apply here because we don't have any prescribed temperatures. What we have instead is a prescribed heating rate and a prescribed convection cooling rate. Okay, and so you make sure that you apply the appropriate boundary conditions that's appropriate to the problem at hand. Okay. Okay. Any questions on this? Okay. All right. So let's go ahead and solve. And so let's go ahead and take our heat equation here, keeping in mind that we don't have any thermal generation. Okay. And so if we get rid of thermal generation, we have 1 over R times ddr of kr dt dr. Okay. And all this is going to equal to 0. Okay, and so let's go ahead and solve this. So first thing I'm going to do is I'm going to multiply both sides by R, just because that 1 over R in front is kind of an eyesore. And so let's go ahead and get rid of it. We have ddr of kr dt dr is equal to 0. Okay. Now that we have this derivative term out in front, we can go ahead and integrate this. And so if we integrate this expression, that integral is going to cancel out with this, ddr. And so we have kr dt dr is equal to integral of 0. Integral of 0 is just 0. But remember, since we're taking indefinite integrals here, we have to add our arbitrary constant. Okay? And so the right-hand side just becomes C1. All right, next thing I'm going to do is I'm going to divide both sides by kr just so I can isolate the dt dr. Okay. And so on the left-hand side, we have dt dr. On the right-hand side, we have C1 divided by kr. Okay. What you might see me do sometimes is that, because k here is just a constant, I can say that C1 is just going to absorb K. Okay, and so we can just kind of get rid of it. Okay. Because we haven't specified the value for C1 yet. And so we can say that C1 is going to absorb just any other constant, just to make our lives a little bit easier. But if it makes more sense to keep it, then you can just keep it there. Okay? And in fact, for this one, I'll go ahead and just keep it just so you can see. Okay. So now that the dtdr is isolated on the other side, we can go ahead and integrate again. Okay. And so we're going to get our expression T of R is equal to, we have integral of C1 divided by R, and so that's going to be C1 over K, natural log of R. And then to that, we're going to add another arbitrary constant, C2. Okay. So this right here is our general solution. So always immediately after you solve your heat equation, you're going to end up with a solution like this, And we call it general because, we have these arbitrary constants, C1 and C2. Okay, so those don't have values yet. And so the way that we specify their values is by applying our boundary conditions. Okay, any questions on this? Okay, so let's go ahead and apply our boundary conditions so that we can solve for C1 and C2. Okay, so first boundary condition, I think the easier one to apply is going to be our prescribed heating. Okay. Okay. And so our prescribed heating is that we're going to take minus K times A, okay, times dTdr. And so we have dTdr. dTdr is actually given by this expression right here. Okay, so dTdr is just C1 divided by K times R. Okay. And all of this is evaluated at Ri. Okay. And this is going to be equal to Q naught. So all I did was I just took my boundary conditions and I plugged in for dTdr, just because we got that expression just from our heat equation integrals. Okay, so let's go ahead and simplify this. And so we have K up top, K in the bottom, and so that's going to cancel out. And so it's actually kind of nice that we left in there. Okay. For R, remember, anytime you see R, we're going to plug in Ri. So that's what this represents, right? And so whenever we say evaluated R is equal to Ri, that means we just plug in Ri in for R, okay? But that's not the only thing we can plug in here, right? We can actually plug in an expression for the area as well, okay? And because if you remember, usually when we talk about, convection or conduction on a surface, we're always looking at the surface area, right? So this A here represents the surface area. Okay. And here we're talking surface area of a cylinder. And so surface area of a cylinder is 2 pi times the radius times the length. Okay. Where again, we have an R here. And so we're going to evaluate that R at Ri. Okay. So the A here is 2 pi Ri times L. All right, so if we make all those substitutions, what we get is minus 2 pi Ri L, okay, times C1 divided by Ri this is equal to Q naught. Okay. The Ri's here are going to cancel. And so what we get from this is C1 is equal to Q naught divided by minus Q naught, 2 pi L. All right, so that's C1, and so that's our first boundary condition. Next one that we're going to apply is our convection type boundary condition. Okay. Okay. So let's go ahead and do that. And so our convection type boundary condition, we have a minus K times A dt dr. Okay. Everything here evaluated R is equal to R naught or R0, okay? This is equal to H times A times T at RO minus T infinity. All right, so let's go ahead and simplify this. Okay. So I'm not going to plug in for A here. Normally you would plug in for A is equal to 2 pi R naught times L, but we have an A on the left and A on the right, and so those guys are just going to cancel out. Okay. On the left here, we have a minus K times dTdr. Okay, so we have a minus K. dTdr, the same as up here, is going to be C1. C1 divided by KR. And in this case, since we're evaluating it at R is equal to R naught, I'm going to plug in C over K1 R0. Okay. It's supposed to be RO, but I keep saying the wrong things like over and over again. It's not R naught, it's R0. It's not R naught, it's RO, not R0, RO. Okay. And you get more sleep. Okay, and on the right here, we have H times T at RO. And so RO is given by up here, T of RO. Okay, so this is C1 over K times the natural logarithm of R. But instead of R, we're going to plug in RO, okay, plus C2 minus T infinity. And so everything that I've bracketed there is T at RO. Okay. I'm going to leave things in terms of C1. And so I know we solved for C1 already, but you know, it's going to be a pain to plug it in. And so let's just go ahead and simplify this and solve for C2. Okay, because that's all we need. Okay, and so on the left-hand side of the equation, we have the K's are going to cancel out. And so if we divide both sides by H, we have a minus C1 divided by HRO, okay? Okay, and on the right, we have a C1 divided by K, ln of RO minus or plus C2 minus T infinity. And so let's just go ahead and solve for this. And so we move this, we move the T infinity. We're going to go ahead and add and subtract that to the other side to isolate C2. Okay. And so what we get is C2 is equal to C1 times minus C1, 1 over HRO plus ln of RO ln of RO divided by K plus T infinity. Okay. Let me go ahead and plug in for C1. And so we plug in for C1, then we get C2 is equal to, the negatives are going to cancel out, and so we have Q naught divided by 2 pi L times 1 over HRO plus ln of RO divided by K plus T infinity. Okay. All right, so now that we solve for C1, C2, the last thing to do is just plug it back in. And so you can take these C1, C2 values and plug it back into our general solution up here. Okay. And so once you do that, that's the end of the problem. And so, you know, we are a little bit short on time because I want to make sure I get to as much review as today as possible. And so I'll go ahead and leave that to you. But of course, this example is already also worked out in the lecture notes. And so if you look at lecture note 02, the example is worked out there. Okay, but that's a review. I think that's a good example. So that's a good example of a heat equation type problem. You know, we did kind of everything here. So we started from the problem, we stated our assumptions, we stated our boundary conditions, we solved the differential equation for the heat equation. We got our general solution, we applied our boundary conditions, and then through the boundary conditions, we got our specific solution. Okay. So I think that's kind of a good review of that. Any questions on this? Good. Okay. All right. And so so I think that's a good review of heat equation type problems. Next thing I want to go over are thermal circuits. Okay. And so I don't really have too much to say about thermal circuits, just because, you know, we've been working on it a lot through this semester. But I do want to remind you of certain facts and a certain key concept that I think is important for radial systems in particular. Okay. And so I think the thing that we may not have seen for a while is, you know, the conduction resistance of a cylindrical system and the conduction resistance of a spherical system. Okay, so let's review those first. Okay. And so if you have a cylindrical system, and it only works if you have a hollow system, you have a radius, we have an inner radius R1 and an outer radius R2. Okay. And so if we're interested in computing what's the conduction resistance, or how much resistance to conduction that we have in between these two radii, okay, and so in basically the solid that I'm coloring in right now, the conduction resistance for this is we take the natural logarithm of the outer radius or outer diameter divided by the inner radius or inner diameter, okay? And then we divide this by 2 pi times the thermal conductivity of the material times L. And so if you were to come across a system, you know, a cylindrical system, and you wanted to represent the conduction resistance of a certain layer, usually this layer represents some kind of insulation, and so maybe some kind of insulation on a wire, insulation on a pipe. This is how you would do it, or this is the equation that you would use. Okay. All right, so now let's review the one for the sphere. Skip ahead in the notes, just so I get it right. All the way in the back. Okay, it's right here. How does that even happen? Okay, and so for a sphere, you know, just because of my excellent drawing skills, it's going to look the same as the cylinder. Okay, and so we have an inner radius and an outer radius. Okay, so I know they both look like donuts, but just use your imagination that this is like a Whopper or something. It's the inside of a Whopper. Okay? Okay. And so if you have a spherical system like this, then the radius of that, or not the radius, the resistance of that sphere is given by, you take 1 divided by the inner radius. Okay, so in this case, it's R1, 1 over R1 minus 1 over R2, and you divide it by 4 pi K. You have to be a little bit careful here. And so for the cylinder, the outer radius goes kind of first, right? So the outer radius goes on top, but for the sphere, the outer radius goes second because of the 1 over. Okay. And if you ever come across a situation where you don't really remember which radii should go first or which diameter you should put first or on top, just know that thermal resistances are always positive. And so if you get a thermal resistance that's negative, then you're going to probably have to flip the sign somewhere, flip the direction of of the operations that you're doing. There's no such thing as a negative resistance. And so, if you ever get a negative resistance, just, probably you should check your work for something. Okay, so those are our two expressions. I think that's about as far as we have to review, just because, we've done thermal resistances a lot. But there are some, I think, thermal circuit type problems that we haven't seen in a while that I want to kind of remind you what you should do in those situations. And I want to go over just the concept of the critical thickness, which I think was a key concept here as well. Okay. All right. So first, let's go over some thermal circuit type problems that's easier to do with thermal circuits relative to heat equations. Okay. Just want to draw a P. Okay. So there's one in particular that I want to review just because it's been a while since we've done this. But this was something that we did a lot, in the very first part of the class. This was using thermal circuits to find the temperature at a specific location or specific threshold in the circuit. Okay. Okay. So let's say that we have kind of a multi-layered system. So let's say we have, something looks like this. Okay. And so how many layers do we have here? We have layer 1, 2, 3. Okay, so we have 3 layers. And so let's say that in this situation, we know the outer temperature here. Okay, so we'll call that TO. And we know the inner temperature, TI. Okay. Based on the situation and based on the fact that we have 3 layers, we can make a 3 resistor circuit to represent this situation, right? So we have TI. So we're going to have TI on the left end. Okay, we're going to have 3 resistances, and at the end of the circuit, we're going to have TO. Okay. Right. And in between there, we have R1, R2, R3. Okay, so those are all the resistances that are going to be there. Okay. All right. So R1, R2, R3, if this were a cylindrical system, you would use the Ln formula. If it was a spherical system, you would use the 1 over R formula, okay? But what those are isn't that important for this. And so I just kind of want to remind you, let's say that the problem asks you, even though the temperature is at the 2 ends, maybe we're interested in the temperature right here. Okay? We can use the circuit to do that because what we say, remember, what we always assume is that if we have a series circuit like this, then the heat transfer or the Q throughout this entire network of resistors is the same all throughout. And so what we can do is that we can use our thermal circuit equations. We can say that Q is equal to the difference in nodal values. And so here's going to be the difference of Ti by To. And then we're going to divide this by all the resistances in between. And so this is R1 plus R2 plus R3. Okay. Okay. So we can compute that because we know both the nodal temperatures, and more than likely we can compute all the resistance values. Okay. But if we call this temperature here, we call this T question mark. What we can say is that this same Q, another way that we can express it is we can express it as a difference between any two temperatures in the system. And so if we say Ti minus T question mark, okay, divided by the resistances in between. And so if you look at the resistances between Ti and T question mark, the only resistance that we have there is R1. Okay. And so the key here is that these two Qs are the same. Right. And so if you get a problem which asks you to solve for the temperature somewhere in the middle of the circuit, you should take kind of a two-step approach. And so the first step in the process is to compute kind of this overall Q. Okay. And then the second step is to use that same Q to compute the unknown temperature. Okay. Right. And so if you want a good example of this, I think there's a really good one on homework 2, which involves insulating that really hot pipe. Right. And so if you remember that problem, that was one where we kept adding layers of insulation. We kept adding the spray paint insulation. So that's a good one to look at for something like this. Okay. Another type of thermal circuit problem that you might encounter is one that was actually on midterm 2. And so if you remember on midterm 2, what I asked you to do was I asked you to use the thermal circuit to solve for some kind of physical property of the system. Okay. Okay. So this can be anything from like length, like radii, and sometimes even thermal conductivity. Okay. And so in those problems, it's going to be important for you to plug in, the actual expressions for the resistances. Because if you look at the expressions for the resistances, these contain all of those physical properties, right? So we have K, we have L, we have radii, okay? And so I'm not going to say too much on this just because, I kind of just tested you on it, but, just to remind you, plug in And so you're going to form a heat transfer equation just like above, okay? But the unknown in that equation is going to be something within the resistance expressions, right? So it's going to be a length, it's going to be thermal conductivity, something like that, okay? And so if you're curious how to do those types of problems, then you should definitely look at the solutions from midterm 2, because that's a good example of that. All right, any questions on this? Okay. All right, so one last key concept, and I apologize. It looks like we're not going to get to too much radiation exchange, but what I do want to go over this one because it is really important for radial systems, the concept of a critical thickness. Okay. Okay. Let me go ahead and draw something like this. Okay, so here is a typical radial system, right? So this could be a cylinder, it could be a sphere, okay? Right, we have an inner radius Ri and an outer radius Ro, okay? And so in between Ri and Ro is some kind of solid material, right? Most of the time, you're gonna be looking at these situations, you know, this solid material in question, right? So the one I'm highlighting in purple right here, this is some kind of insulating material. So it's some kind of material that's meant to kind of increase the thermal resistance of the entire system. Okay. Because usually what you're going to have is that, you know, on the very inside of this, right, what I'm highlighting in blue, right, this is usually going to be some kind of, you know, it might be like an electrical wire, it might be like some kind of hot pipe, or it might be like, you know, a pipe in your house, okay? And so most of the time, you know, you want to add insulation on these types of systems to prevent heat from going in and out. Okay. But what's really interesting is that sometimes, you know, if the situations are right, you know, for a radial system, if you add insulation thickness, or if you add insulation to these systems, it might actually decrease the overall thermal resistance. Okay? And that might seem very paradoxical at first, because, you know, if you consider, you know, the conduction resistance, and so we've just written this down. So the conduction resistance in this situation is ln of Ro divided by Ri divided by 2 pi KL. Okay. If you take Ro and you increase it, okay, you increase Ro by making the insulation thickness, you know, thicker, right? Then this conduction resistance is going to go up, right? So you have ln of some number, you take ln of some bigger number, then R is going to be bigger, right? And so that makes perfect sense, right? So how can this be? How can it be that sometimes when we add thickness to a system, it actually decreases thermal resistance? Well, because usually on the outside of the system, it shows my colors poorly here. Okay. We'll have Nickelodeon slime on the outside. Right. On the outside of this system, we also have convection. We usually have some kind of convection cooling, right? whatever, you win. Okay. We have convection on the outside, despite what the iPad wants to write. Okay. Right. And what do we know about convection resistance? Right? We know that convection resistance is 1 divided by H times the surface area, okay? Where the surface area for a, I guess we're working with cylinders here, although the same thing applies for spheres as well. Okay, the surface area of a cylinder is 2 pi times the outer radius times L. Okay. The key part to focus on here is R naught, of course, or RO. And so here, unlike the conduction resistance, RO is in the denominator, right? And so if we increase RO, right, we increase the size of our denominator, then our overall convection resistance is going to go down, okay? And so, we have kind of two things going on. So if we increase RO, we're increasing conduction resistance. That makes sense because we're increasing the amount of physical matter that's inside our system, but we're also decreasing the convection resistance, okay? And why is that, right? The reason you kind of have these two competing effects is that when you increase the outer radius of a radial system, okay? When you increase the outer radius of a radial system, you're also increasing the surface area, okay? Okay. And that's really the key point. That's really the key point right there. Okay. And so if you increase the surface area, you kind of increase the opportunity for convection to, take away heat from your system. Okay. Right. And so in radial systems, we have this concept of a critical thickness. And so at the critical thickness, we kind of reach a minimum in the overall thermal resistance. Okay. And so if you recall, we explained this concept with this kind of graph right here. And so on the one hand, we have RO. Okay. And on the y-axis here, we have total resistance. Okay. At first, if you increase RO, the total resistance is actually going to decrease. Okay. And that's due to the surface area effect, right? And so even though you're increasing the conduction resistance, the surface area is growing at a much faster rate that you end up with a lower resistance. Okay. But eventually, as you add more and more thickness, the conduction resistance tends to take over. Okay. So after it kind of reaches a minimum, then it kind of recovers and goes up like that. Okay. And so I think the scientific name for this type of graph is called a bathtub graph, because you can imagine that's the shape of a bathtub. Okay. And so this point right here, where the thermal resistance reaches a minimum, we call this the critical thickness. And so I think that concept is important to know, because this is something that we don't see in planar systems, right? Because in planar systems, if you have like a planar wall, right? So if you think of the wall of that wall back there, right? If we wanted to prevent more of the heat from coming in, then we just make the wall thicker, right? So we make the wall thicker. It doesn't really have any negative effects, right? I mean, other than cost, I guess. But you know, we make that wall thicker. It's going to insulate this room a lot better, and there's really no competing effects. But you don't have that effect. But you don't have that same thing in radial systems because you have this kind of competing interest of, you know, surface area versus thickness. Okay, and so I think that's a pretty key concept to know from radial systems. Okay, any final questions on this? Okay, so I apologize, you know, we didn't get to radiation exchange, although I did want to make sure I cover radial systems thoroughly because that one kind of ran away with the poll. So that was kind of the significant winner from everything. Okay. All right, so we have 5 minutes left, and so, you know, I'll go ahead and stick around if you have any more questions. But, you know, before we go, since it's the last time, you know, I'll see each other before everyone is really nervous for the exam. I just want to say thank you, everyone, for a great semester. I know, you know, this last 2 years have just been weird as hell, and so, you know, we haven't really had a normal semester in a while. And so, you know, I always, you know, want to thank you guys just because you guys are always really patient with me. You guys listen to me, you know, you guys do the work that I assign. So, you know, thank you everyone for a great semester. You know, I know I'll see a lot of you guys next year because, you know, I know some of you guys have already talked to me about, you know, finite elements and things like that. But even if I don't have you in a class again, you know, I'll see you guys around campus, and, you know, don't be afraid, say hi. You know, I'm always happy to see you guys. Yeah. I've talked to the department chair about it. He said, let's wait a little bit because we do need a bigger room if we're gonna extend the class. And so I'd like to move it into 304 because 304 is a much bigger room. But he said, we're gonna wait and see. All right, so thank you, everybody. You know, hope you guys enjoyed the class, which is very easy for me to say because the next time I see each other is going to be the final exam. And so I know no one's in a very good mood right now, but you know, just want to say it was a great semester. So thank you guys. I'll see you guys around. And if you have questions or anything, just let me know. Yeah. Yeah, because if you add thickness to a radial system, you know, you are increasing the thermal conduction resistance, but you're also increasing the surface area. And so, you know, you don't get the same kind of one-to-one effect because if you make that wall twice as thick for a planar system, you're going to get twice as much insulation. But for a radial system, if you make the radius twice as big, you may not see twice as much benefit because you also increase the surface. That's kind of what it is.
Oh, okay. Have you heard of a good notes?
No, I haven't.
It's very, very good. Like,
Oh, okay. Yeah, I'm using OneNote. I think the issue is with my Apple Pencil. I think this thing is like
actually, I used it too, and it lagged on my notes. So
Really?
I switched over to Samsung. I have a cheap tablet.
Yeah.
So like this one's free on here, but I'm not sure they have Samsung on Apple.
Yeah.
But she writes down like the Resistor has it.
Okay.
And she said it's really good for drawing, and then it's like you buy it with the group of friends, it'll be much cheaper.
Okay.
Yeah.
Okay. Yeah, maybe I'll check it out over summer.
Stress concentration.
So because of increase in surface area.
Right.
But it depends, but it can be also TFS if it's rotational torsional.
By chance that you get them like less than one or your factor safety on the first one?
I didn't finish that. Dude, the first one I skipped it because
Sorry,
I was all shit.
Okay.
I forgot how to.
So can you explain the heating on inside versus outside for like
Wait,
power generation?
Oh, yeah. So I think the question for that was, you know, what's the difference between heat flux and thermal generation? So heat flux is always applied at some boundary. So it's not really outside. It's just whenever you have a boundary on the building. And so here we have a cylindrical system, and we have two boundaries. So we have one boundary here at R naught and one boundary here at.
Well, I understood a little bit, but.
And so heat flux is always going to be applied at one of these boundaries. So in this case, we are applying it at the boundary of Ri.
So I couldn't study for.
Whereas the thermal generation will occur throughout the entire volume. And so, kind of like the, kind of the verbiage you should look for is that, the material itself produces heat, or the material itself absorbs heat, or if the material like has some kind of chemical reaction. And so heat flux, heat flux is something you can apply from the outside. So if you have like some kind of heater, you're feeding it from the outside, that would be like a heat flux, thermal or a specified heat transfer.
Is it kind of like a fan? Like,
Not really. And so, because I know the verbiage gets a little bit confusing. Because, when you think of thermal generation, you think of like heat being generated, but you have to ask yourself, where is the heat being generated? If it's actually being generated within the solid itself.
so like between this region and this.
Exactly, right. And so the only way that can happen, and so physically the way that would happen is that if this kind of plastic cover right here, if this was generating heat on the inside, which actually, in reality is very rare. So it's very rare to have a material that can produce heat like that. And so for a lot of situations, you're not going to have the Q dot. And so the only time you would do that is if you have some kind of reacting material, some kind of material that can either absorb heat or absorb heat.
So just to confirm, what if it's happening on the inside, then I don't count it? It only counts if it happens between here and here?
Yeah, so if it's between here and here, then it would be a Q dot, right?
Okay, let me.
So that would be, so if it's within the domain, you would account for it actually within your heat equation itself, Q dot. But if it's not, if it's only being heated from the outside, you would include it as a boundary condition.
That's cycle. It says on the sheet. It says right here.
Some guy in my school created dreams about.
So if it's in the domain, then we include it in the heat equation. But if it's not included on the side, but it's included on the outside, then we do boundary condition.
Exactly.
Oh, thank you.
Mhm.
I might ask about that again.
Okay. Yeah. It's the verbiage is a little bit confusing.
Thank you so much.
Yeah. All right, Nick, you still there? Oh, I think the volume's off, but I see that you're talking. I'm increasing the volume.
Can you hear me now? Is it
Yes,
working?
yes.
Okay, cool. So on number 4, part D, we're working with the gray body with that fin. And so I got the Q for the fin, but when it asks to find the radiation heat loss without the fin on the as a flat surface,
Yeah.
I'm having a difficult time finding even a starting point, I guess, to
Yeah.
make sure.
So without the fin, basically you would have just a flat surface like this, right?
Right.
And so what I want you to do is I want you to compare kind of, how much heat transfer you would get from kind of like the same kind of area that would take place. So, that fin, usually takes up an area like this, right? I think this is W and this is H, right?
Yeah.
And so without the fin, it's just going to move over to the right a little bit. To the right, without the fin, we would just have like a kind of a square patch of wall, where the length of that patch would just be W. And so without the fin, it would just be a two surface system. So we have just this one and then the deep space.
So would I have to set up a new resistance, basically? Is that like the way to do it?
Because you guys quiet down for a bit? I can't hear Nick. All right, go ahead, Nick.
Would you have to find set up a new resistance basically for the new system to be able to calculate it?
Yeah.
Is that okay? All right.
Yeah.
That's
So
okay.
yeah, you would just have two, and so you'd have just something like this, right? And so this would be 1 minus epsilon A, and actually, there would be no view factor resistance there, because the view factor here would just be 1, right? Because if you just have a flat surface, then all of that radiation is going to go out to deep space, and so the view factor would be 1 in that case.
Got it. Okay.
Yeah.
All right. That should be good. Thank you.
Yep. Mm-hmm.
All right.
Anyway, Christopher, are you gonna teach 410 next semester?
Most likely. I mean, I haven't gotten the official assignment, but I've taught it 4 times in a row now, and there's no other faculty that are willing to teach it. And so I think there's a 99% probability that I teach it.
And then are you doing any other classes this semester?
I mean, I put in my requests. So usually I teach fluids in the fall, and I usually teach 401 in the fall, one section. Yeah, economics, but I don't know yet. And so it's gonna depend, because I know we have some professors going on sabbatical next semester. Some are, yeah, and some faculty are also leaving, or part-time faculty are leaving. So, you know, I know that they're kind of struggling with staffing, so they might ask me to teach something weird. You gotta talk to Dr. No about that.
Yeah, I think I might have you before 10.
Okay, yeah, I know the wait list is full. I'm trying to get it,
I managed to get in. So.
yeah, I'm trying to get them to expand the class roster, but we'll see. If anything, I usually try to add as many people from the wait list in that class as I can.
Yeah, this. The first one